kind of thing. You don't know that, and depending on your interpretation of quantum mechanics, a lot of people say you cannot even know it. In fact, a lot of people say it's even meaningless, has no meaning. It depends on your interpretation, right? But generally speaking, the Heisenberg uncertainty principle, HUP, prevents you from knowing when this transition occurred from state UK to state UM. Right? That's the probability that it's made that switch, that transition from state UK to state UM during that time interval from naught, time equals naught, to time equals t. Right? Right, now we can get even more nitty-gritty. Now let's actually do an application. We will actually choose a concrete perturbing Hamiltonian H dashed, and saying a bit before, we'll choose to be this one. Why? Because the math is easy, Wales, right? And it has a certain didactic quality about it. Didactic, adjective of concerned with good teaching. It's a good means to, because you can learn from it in that sense, right? So assume the perturbing potential H dashed is of this form. So this part here does not depend on time. This part does. Okay. Now you probably know from theory of complex numbers, you can rewrite cosine in terms of exponentials, e to the I something. I will be teaching a course on complex analysis, a senior M1, sort of mixed. The earlier chapters definitely undergrad level, later chapters analytic continuation, stuff like that, more masters M1 level. So I will be teaching a full course on complex analysis, in other words the calculus of complex numbers, complex functions, differentiating and integrating complex functions, f of z, where z is a complex number, x plus I, y. So I've seen you've done some theory of complex numbers, and you know that you can rewrite a cosine in terms of exponentials, complex exponentials, e to the I something, whatever. Okay? Alright, so this is the perturbing potential, H dashed. We have a formula here, right, that I've just labelled x circle. So we have this equation. We're starting off in the state UK, right, AK is 1. Starting off in that state. And we want to know, we know what H dashed is, we're given that, it's H bar cos omega t, so we can plug in that H bar formula for here and calculate what this is, and hence find what AM1, what this is, right? Now I ask you to do it for homework, so plug this in, but your cos now, expand that in terms of exponentials, in complex number form. And a cosine involves two of these complex exponentials, e to the I something, two of them. Assume you know that, so translate that into this double exponential term. Plug that into here. And you will get, now the H bar, that's just a constant, right? That's just a constant in terms of time. We're integrating with respect to time, so this H bar comes outside the integral. Now do this for homework. So you plug in this with the two exponential terms, you plug it into here, you've got another complex exponential term here, integrate the whole stuff, and you'll end up getting something like this. Well, you should get this exactly, right? So do that for homework. Right? Get this expression. Now, let's start analysing this expression, because what is it? Well, it's the first order correction term to your A coefficient for state M, not state K. Right? M could be a different state. Where we have the possibility now of a transition, switching from state K to state M, and M could be any of those eigenstates. So there's a probability, as long as it's not zero, there's a probability that the system could switch from state K to any of these states M. Right? Now, okay, you get this expression. Now have a look at it and ask yourself, well, this term here is interesting, right? Why? Well, imagine that this frequency, angular frequency, omega here in the perturbing potential, if you like, imagine that it was very close to this value here, right? And this omega mk, that comes from the energy difference, the energy Em minus Ek, the whole thing divided by h bar, right? But if this value here, omega, this one, is close to this, then you get a kind of resonance. What's resonance? I talked about this a bit before. If you blow into a soda pop, empty soda pop bottle, and if the frequency that you're whistling at, can't whistle. So if you choose the right frequency, so if the wavelength of your oscillation fits the dimensions of the bottle, you get a kind of resonance effect. So you get a stronger echo. The bottle will be making the same sound frequency as you're whistling at, right? Sort of resonance. So you get something similar happening here. If this angular frequency omega here is pretty well equal to that. Now, if this is almost the same value as that, well, the difference would be small, right? But it's in the denominator. So if this here is small, this term here becomes very large, right? Hence this is large. In other words, the probability of it switching from state UK to UM is large when you have a so-called resonant adjective, resonant or resonating frequency, right? Or angular frequency, when this omega is close to that. Now, when that's the case, since this is the denominator, this term here becomes large. You can forget about, then you can neglect this term, right? It becomes small in comparison to this one. And then if you square this thing to get the probability of a transition, switching from state UK to UM, so neglect this term when this is close to that, and square it. Again, do it for homework. You'll get something like this, right? So well, you said that's squared, sort of obvious. Why sine? Just squaring it. Why not cos? What happens? You'll have to do the nitty gritty. Okay. So you square this and you get this expression. So this squared is just that, makes sense, h bar squared. Well, you're squaring it, so that makes sense. What happened to the 2? Probably got something to do with the sine. No, why sine, not cos? You need to think about that, right? Maybe it can be eliminated for physical reasons, or is it just come out of the math? Well, yeah, think about it. Okay, so the square of this amplitude, that gives you the probability of getting this switch, and it's this. Now in the next session, now this is an important equation, so I've labelled it x circle. So I've got 2x circles. Well, anyway, so I will, in the next session, I'll actually draw a graph of this expression where, so what am I graphing? So just jumping ahead a little for next session. I will graph this sine term. except I won't put this in, but it'll be sine squared, all this divided by the difference in the omegas squared. Okay? So I'll be graphing this divided by that squared as a function of, that's on the vertical axis, and on the horizontal axis just omega, this function of omega. And you'll notice that this sine squared divided by the difference omega squared peaks mightily at omega equals omega mk, but it's not like an infinitely sharp peak. It is not like a delta function. It is not a delta function. Right? It actually has width, and that's interesting. Physically, that's interesting. Okay. So next session I'll actually show you the graph of this sine squared term. So we're mapping this divided by that, okay, on the vertical axis, and on the horizontal axis, versus omega, and you'll see that it definitely peaks, but it's not like an infinitely thin peak. It is not a delta function, and we'll talk about the consequences of that next session.